Welcome back to the payment series, the only place where bill payments are discussed more seriously than actual bills. If you think payments are simple, I click pay, money magically flies to Electra, lights stay on, end of story. Then buckle up, my friend. In reality, one bill payment triggers a microservice reunion party, Kafka screaming events into the void, a batch process waking up once in a day like a depressed Pokemon, a file upload to a fake central one, and three retries because the universe said no to the first two times. All that. Just so you can keep watching Netflix in peace without your lights turning off. Last video was functional flow, the clean, pretty version. Today is the architecture episode where we expose the truth. Bill payments are held together by engineering duct tape and pure hope. Let's meet the actors in this architecture. First, we have the biller service. This is our official registry of who you are allowed to pay. Add a biller, fetch a biller, check if they are active, simple and clean. Then comes the payment orchestrator, the real brain of the operation. It validates the request, holds the customer's funds, creates the payment record, and drops an event into the outbox. The outbox publisher picks that up and pushes it into the Kafka. No drama, no duplicates. Next is the BillPay Worker. It consumes those events, stores each bill line, assigns a batch, and when cutoff comes, it emits a batch ready event. From there, the settlement service takes over. It builds the pain.001 file, sends it to our mock central one, handles acknowledgements, updates payment statuses, retries if needed, and sends the rest to DLQ if the universe refuses to cooperate. And of course, we have Dummy Central One, our safe, friendly, pretend clearing system that lets us simulate uploads and failures without involving the real Canadian banking system. And tying the whole thing together is Kafka. In this architecture, Kafka is not just a messaging system, it's the backbone of our payment platform. Instead of calling each other directly for every little thing, our services mostly communicate through asynchronous events. Each service emits signals about what just happened, and the other service quietly picks them up and do their part. This gives us all the good stuff. We can scale each service independently. We can retry work without making the customer wait. We keep the customer experience smooth while the back office fights its own battles. And of course, we maintain the illusion that everything is perfectly coordinated because we are a real bank, a serious one. Now, let's walk through each service and look at how they send and consume these events across the system. The bill payment request first meets the payment orchestrator, the microservice that pretends it has everything under control. Normally, your front end would talk through an API gateway, but for today, let's keep it simple and assume the front end just calls this guy directly, which is the payment orchestrator. So, the payment orchestrator first validates the biller. It calls the biller service and asks, is the biller registered? Are they active? If the biller checks out fine, we move forward. If not, the flow ends right here. Next, it asks the account service. Does the customer actually have the funds? If yes, it places a hold on those funds. So the customer can't wander off and spend that money on something else while we are processing the bill. Next, the orchestrator needs to officially record what just happened. So it performs two inserts, both inside a single database transaction. First, it inserts a row into the payments table with the status as funds held. Then, right beside it, in the exact same transaction, the orchestrator inserts another row into the outbox table with the state as pending. Now, this outbox row is important. It's basically the service writing a little sticky note to itself saying, we owe Kafka an event for this payment. Don't lose track, don't forget, don't get distracted. And because both insert happens in one atomic database transaction, we guarantee two things. We never create a payment without an event. And We never send an event for a payment that does not exist. This technique is called transactional outbox pattern, and it saves us from the nightmare known as dual write problem. If we write to save the payment in the database and publish to Kafka separately, there would always be a chance that one succeeds and the other fails, which in banking would create absolute chaos. With the outbox pattern, the database becomes the source of truth. The payment record and the event to be published record either both succeed or both fail as one single consistent unit. Now, at this point, we don't wait for the entire backend circus to finish. We simply send back an HTTP 202 response at this point of time, which says your bill payment is accepted and is being processed, which is a polite banking language for trust us, things are happening. Now enters the Outbox publisher. The Outbox publisher is like a night shift worker. It polls the Outbox table, picks up all the pending entries, and publishes an event called BillPay.requested for every entry in Kafka. Then marks the Outbox row as published. Once the event lands in Kafka, our BillPay worker is already listening like a hawk because its entire existence revolves around processing these messages. It has two main responsibilities. It consumes the event and record the bill line. As soon as it gets the message, the worker saves the bill line into its own database. It assigns a batch ID because bill payment travels in groups, like school kids on a field trip. Nobody goes alone. At this moment, BillPay Worker emits an event called BillPay Enqueued, which is consumed by the Payment Orchestrator. Again, we have the Payment Orchestrator here, which consumes this BillPay.enqueued event and sets the business state as batched. So this step basically says, okay, we know who you are paying, how much you are paying, and we have parked the money. You are in the system. The second responsibility of BillPay Worker is that it waits for the magical moment called the cutoff time, like 4 p.m., when it wakes up and says, all right, everyone gather up, we are going as a group. So it collects all pending bill lines, groups them into a batch, and emits an event telling settlement bill batch ready. Settlement service is the part of the system that actually talks to the outside world and therefore has the highest stress levels. It listens for bill patch ready event and takes it up from there. It builds a pain.001 file. First, it grabs the entire batch and turns it into that file. You can think of pain.001 file as the former envelope we send to Central One. It's our way of saying, here are all the bills we would like to pay today. Please don't reject them. Then the service sends that file to the dummy Central One system. In real life, this would be an SFTP, an API call, or whatever Canadian banking magic is using that week. As far as we are concerned, we use a mock system for demos. If the upload succeeds, settlement emits an event bill batch submitted. Payment Orchestrator is listening to this event and updates the business state as submitted. It means your batch has officially left the building. Later, when Central One sends back a response, in our case a simulated pain.002 file, the settlement service processes that file and goes through each individual record. For each payment line in that response, it emits a BillPay.status event indicating whether that specific bill was posted or failed. The payment orchestrator is listening to this status and updates the business state accordingly. If the state is posted, it means the payment is fully successful The orchestrator then releases the hold and performs the actual debit on the customer's account. If the status is failed, the payment did not go through. In this case, the orchestrator simply releases the hold. No debit, no money leaves the account. This is how we close the loop. Settlement confirms the outcome, and Payment Orchestrator finalizes the customer's funds based on that result. Now for the chaotic part, retries and DLQ. Settlement handles all the retries itself. It tries the upload up to 3 times. If it still fails, the service throws up its hands and emits a DLQ event. The DLQ is basically our parking lot of problematic items. We don't delete them, we don't ignore them, we simply mark them very clearly and say, please investigate this mess. This gives us reliable settlement, clear error handling, and a clean flow from batch creation to final posting. And that's the complete event driven architecture behind our bill payment flow. Kafka is the backbone, biller, orchestrator, outbox, bill pay worker, settlement, and dummy central one. Business states like funds held, batched, submitted, posted, failed, and clean retry plus DLQ handling built into settlement itself. In the next videos, we'll go screen by screen and code by code so you can see how all of this is implemented in Spring Boot and Kafka. Because talking about architecture is fun, but shipping code that actually pays an Electra utility bill, that's where the real satisfaction is. So, see you all in the next video.